Hi girls! Today we're going to look at how to make sure we've linked our observations and the products of our redox reactions. Now this is very much a recap of level 2. This is exactly what you had to do for your level 2 assessment. So hopefully it won't take long to go through and most of you will be familiar with the concepts. So the first point to note is that you do get a resource sheet or some resource information with your assessment, so you don't have to memorize all the colours and all the reactants and products. You just need to be able to actually make those links correctly. So the key thing is to know is that many species have different colours for different oxidation states, particularly in the transition metals, but to a lesser extent in other species as well. Most of your coloured compounds tend to be your transition metals, and the reason for that is all about the electron structure of transition metals, which we might get into later. However, just be aware that they are different colours. You've also got different states, so it could go from a solid to a liquid to a gas. And so by making those observations and knowing what's actually happening in our reaction, it's often possible to identify what the products of our reactants are. So we know what the observations of our reactants were, and we can figure out what our products must have been based on the observations. Sometimes that's going to be really obvious, sometimes it's not, so we have to do a little bit of detective work and a little bit of logic. Okay, so just a couple of examples. So we know that copper metal, for example, is a browny orangey pinky solid, while copper 1+ is a brick red solid and copper 2+ is a blue coloured solution. Iron could be a silvery coloured metal if its oxidation state is 0, but iron 2+ is a pale green and iron 3+ is an orange-brown colour, rust colour. We know hydrogen is a gas and H+ is an aqueous solution. Permanganate, or rather the various species of manganese, are probably some of the most interesting ones. You will all be familiar with permanganate, which is MnO4-, that's that purple solution. And you know that when it reacts in acidic conditions, it forms Mn2+, the manganese ion, which is a pale pink or usually colourless solution. But you've also got other ions as well. Manganate is green, manganese dioxide is a brown-black precipitate, and of course you've got pure manganese metal as well. So just to show you some images for a moment, these are the different species of permanganate, or manganese I should say. So on the left-hand side, you have Mn2+. The two in the middle are your manganese dioxide. One's a pure sample of manganese dioxide, and the other's what it looks like when you form it in a reaction. The greenish coloured one on the right-hand side is your manganate ion, that's MnO4 2-. And then, of course, on the far right, you've got your traditional permanganate. Now, having some understanding of what these compounds look like, not necessarily just the permanganate ones, but in general, means that when we look at a reaction, we can actually make some assumptions about what's happening. So if we can imagine here for a sec, this is an experiment that you have all seen and done, but I'll just go over it yet again. In the left-hand test tube in this image, you have an iron nail sitting in a test tube containing copper sulfate. So you've got copper 2+ ions in the solution, which is blue, and you have the silvery coloured metal that is iron. The image quality is not the greatest, so you can't really see the colour that well, but trust me, it's silvery coloured. If you leave that for a time, and you really are looking at least a couple of days, what happens is it turns into the solution on the right. You've got a solid amount of a brownish solid forming around the outside of the nail, and the solution has turned from an orange to a green colour. Now when you look at that, you can actually realise that the copper 2+ has been reduced to form copper metal, while the iron has been oxidised to form Fe2+. You know it's Fe2+ and not Fe3+ because the solution is green. If you leave it for long enough, it will turn into Fe3+ and go a brownish colour, but at this particular intermediate point, when this photo's been taken, it's actually at that Fe2+ solution. So by looking at your observations, it can tell you what is actually reacting, or what your products of your reaction are particularly. You know what your reactants are usually because you've already made them, put them together. So making good observations of both your reactants and your products is a really, really key skill, and then linking those observations to identify your reactants or products is the next step in the process. This is all stuff you did last year, and so I hope it makes sense. So really what we've covered now in terms of oxidation numbers, what's been oxidized and what's been reduced, observations, balancing equations, is largely what you had to do last year in level 2. So I just want to show you a quick link to some practice that you can do. This is the Science Scribe website run by Lian So, who used to work at Karanui College in the Wairarapa, but is now working for SciPad. And if you go along to this website and you have a look, there's a little tab here, Level 2 Chem, and you choose that. And you go down and you look at oxidation reduction. There is this web project Excalibur. This is really good practice. So when you jump into Project Excalibur, and this is slightly being cut off this video, but up in the top left-hand corner, if you come and have a look at this yourself, there are 2 boxes, LU, which is look up, and QU, which is generate a random question. So you can choose the question. Okay. And here's your question. So drops of iron sulfate are reacted with 3.5 mils of bromine water. The orange solution begins decolorizing. So the first thing to note is that your bromine is being reduced to form bromide because the orange is disappearing. Therefore, your iron 2 must be being oxidized to form iron 3, and so you can write balanced equations. You can write half equations, make observations, figure out oxidation numbers and electrons, and up here at the top was a 0.5, a 1.0, an OB, an ON, and an E-. So when you look at the 0.5, it shows you the 2 half equations for what's happening. The 1.0 shows you the overall full equation. The OB shows you the observations. Orange bromine reacts with pale green Fe2+ to form colorless Br- and orange Fe3+. Oxidation numbers linked into that, and a discussion of the electron changes as well. So this is a really, really useful website for some practice about how these actually go together. So making sure you can accurately link your observations to your reactants, products, half equations, electrons, oxidation numbers, etc. All right, so next lesson we are going to be moving on to electrochemistry, which is something completely different. So please make sure that you are up to speed with all the stuff we did last year, and then we can get on to the new stuff next time I see you. Thanks very much, guys.